That was Gustav Holst's Jupiter. Now we have Bart Howard's Fly Me to the Moon. Fly me to the moon. Let me play among the stars. Let me know what spring is like on Jupiter or Mars. In other words, hold my hand. In other words, darling, kiss me. Fill my heart with song. Let me sing forevermore. You are all I long for, all I worship and adore. In other words, please be true. In other words, I love you. And now we're coming into Kathleen Astor. was Kathleen Astor, followed by Fairy Dance. As soon as I get this, I'll be right back. Music. I have a little piece on Cullen's Thankful Tea. So change to B flat. I am playing a lever 40, Prelude lever 40 harp. And I changed the notes with levers on the top. And if I had a pedal harp, I'd be changing notes on the bottom with my feet. Let's see. Okay, here we go.
Hi, Kim.
Yeah, is it?
Yeah,
Is it?
it's 7:29. So unless you got something really fast.
No, I'm all that's a wrap.
Well, thank you so much again. That was really great. Really appreciate it.
Thank you.
And it's now about time to start our April meeting. So may I welcome all of you to the April meeting of Orange County Astronomers. We've got a great lineup as usual of both one of our favorite What's Uppers, John Garrett, and a great speaker. And I think all of us are really looking forward to it. I know that April is a busy month for many of us, or this whole springtime is. There's a lot going on. And I really appreciate the fact that you're making time for us. It's good to see so many names on the list of participants. And I hope that you enjoy it and that you let other people who might be interested know about it as well. We're continuing to do these Zoom meetings indefinitely, even when we are finally able to start having our meetings in person again. We expect that we will still be doing things online. So hope you enjoy it, hope you take advantage of it. And with no more ado, I will turn it over to Kyle for the announcements. Welcome, Kyle, from back east, right?
Yeah. I will, let me share first. Here we go. This is the right one. All right, here we go. Right, so the April announcements. Welcome new members. You should all be receiving your new badges in the mail at some point, probably within the next month or two. The ANZA site, there will be a star party. Star parties are starting up again, in-person star parties. The first one will be on May 28th, so stay tuned for more information on that. The Orange County Star Party is still on hold. The Astrophysics Special Interest Group meeting, their next meeting is on April 29th at the Heritage Museum, and that will be at 7:30. The beginners class is still online. That is May 6th, along with the board meeting. The next board meeting is May 15th. That will also be online. And consult the calendar to see more information about the events. Coming events, the Carnegie Observatories are having a lecture series in April and May. You can do it either in person or online. Registration is free, but the number of tickets is limited. So please check out the link below for more information.
Oh, good. There's the announcement. We just got news a couple of days ago that we're cleared to have a visit up at Owens Valley Radio Observatory, our usual type of thing, in June, on the weekend of June 24th, 25th, and 26th. So we'll do our usual stuff, astronomy on Friday and Saturday nights, and then a tour on Saturday day starting at about 1 o'clock. So if you're interested in coming, either call me, there's my phone number down on the bottom of the slide, 562-810-3989, or you can email me, just think of Flash Gordon, Dr. Zarkov56 at yahoo.com. I'll put you on a list, and when I know exactly the details, I'll send you the information you need to be able to go along. It's free. All we need to do is show up. There's 110 volts, 220 and 440 if you need it, depending how big your telescope is, and bathrooms and kitchens and motels. And so we're ready to go. Glad to have everybody along and looking forward to it. Thank you.
Great. Right. Another program for any number of participants. I know they sent this out to the University of Maryland Astronomy Department because I saw this last week in my email box. The Summer Observational Astrophysics Retreat is going to be at Mount Wilson for the last 2 weekends in July. There's some more information on this slide. Please check out that website if you are interested in possibly going to that. The review of applications will begin on April 15th, and people will be admitted on a rolling basis until spaces are full. And outreach events are up and running again. Currently, we're looking for volunteers to go out to these events. So if you are interested in doing that, please contact Cecilia for more information about that. Again, the Adopt a Scope program, which I believe has been mentioned recently, that it was on hold. Now it is up and running again. There's some information on the slide. If you go to the resources tab on the website and go down to Adopt a Scope, there will be a whole web page here of information about the scopes available that are currently in inventory, along with the process for being able to acquire one of these scopes. So check that out for more information if you are interested. If you have any items of interest to put in the Serious Astronomer newsletter, please contact Dave Fisher and he will review those items. If you want to only receive your Serious Astronomer newsletter via the e-version and not receive a printed copy, please email Charlie and he will stop sending you one. Again, everyone gets a paper one unless you opt out of receiving the paper version, but everyone can also access the newsletter online through the OCA Astronomers website. Please remember to keep weeds clear at ANZA. And then the What's Up presentation by John Garrett will be next from the Temecula Valley Astronomers. Thank you.
Was always my most dreaded sky when I first took up amateur astronomy, and I'd go to our club star parties because I always felt there was just so little bright, easy to find, crowd pleasing objects in the spring sky. So I used to be terrified of it. But ever since I learned how to use my telescope mount properly, now I'm finding the spring sky extremely exciting and overwhelming with how much there is to see. And so I'm going to share a little bit of that, as well as the highlights of the month, the changing highlights, such as the moon. So starting with the moon this month, we are approaching a first quarter moon tomorrow. And then following weekend, we'll have a full moon. And the next 2 weekends in April, we'll have the third quarter moon and the new moon. And those coincide with weekends. And so if you're like me and your only free time is on weekends, those are going to be good times to get out under a dark sky to look at the spring sky. The first of those darker weekends is a third quarter moon, and you can expect the peak of the Lyriad meteors. And the Lyriads go on from the 14th to the 30th, but the peak is April 22nd, the early morning hours. That's also my wife's birthday, so I naturally invited her to join me for the Lyriad meteor showers out in the desert, but I'm still waiting for an answer on that. But I recommend giving it a try. Here's a Lyriad I caught 5 years ago, and I've since then read that the Lyriads are noted for either fiery trails or good debris trails. And in fact, I actually don't remember what I read, just that I read one of those or both of those. And this photo I got of my only Lyriad meteor is kind of supports both of those. And when I got this picture, I saw it on my camera display screen, and I noticed it had something interesting going there. And so I continued to take 30-second exposures, about 30-second exposures for the next 10 minutes, and captured the debris trail of this meteor as it changed shape, obviously probably by the winds and the different altitude that debris trail probably passed through winds of different directions, making it look a bit like a golf club or a hockey stick shape. But I recommend getting out that weekend, trying for the Lyriads. And so again, we have a third quarter moon. So typically meteor showers are best in the morning hours, but that one will be compromised by a third quarter moon, but you still may be able to see bright lyrids. And then the evening before that is also a good time to be looking and to set up your camera for wide field views and see if you capture some of those. According to Astronomy Magazine, there's a comet. Since I haven't seen the comet and it hasn't been showing up yet in the northern hemisphere, I'm going to list it as a maybe, because new comets, it's hard to know for sure how they're going to turn out. Last weekend, I photographed this picture. I was staying at Red Rock Canyon outside of Las Vegas on a climbing trip. And so I got this picture of the sky. And by the way, these rocks here that you see so nicely lit up, those are lit up by the sky glow of Las Vegas. But in this picture, you can see that Orion and Taurus are in the southwest, low to the horizon. And about where I captured this airplane in motion, that's about where I estimate the comet C2021 Pan-STARRS comet might become visible later in the month. So between the 25th and the 30th, keep an eye on the Pleiades. If you can see the Pleiades, it may be wise to also look for the comet. I don't know what magnitude they expect it to be. I've seen, maybe 10th magnitude. So maybe it'll be binocular visible, or maybe it'll get nice and bright and surprises. So that is something to watch out for. But the usual caveat, I don't know what comets are going to do. And I've had many of them fizzle after I told people, go see this comet. Conjunctions. I meant to get up early in the morning today and take a picture of the morning sky, but I have to do a mea culpa. I slept through this morning, but someone sent me an email with a fine picture from Sky and Telescope of the 4 bright planets in our morning sky and where you may find the moon near them toward the end of the month. So those will be some nice things to get up, but I'm in no position to tell you to get up in the morning and get that view. But if you do, these treats may be worth your time. The constellations, I got out 2 weeks ago at Anza Borrego and took some pictures. I meant to take some to set up a telescope as well as wide field pictures, but it was so windy. All I could do is set up my wide field camera, which I will share the results of tonight. Here's a picture of Canis Major, pretty low in the south. And Canis Major has the winter Milky Way. And this time of year, you can see the entire winter Milky Way in the early evening. It forms an arch over the western horizon. And so I'm going to follow in my pictures the winter Milky Way from Canis Major to the left of Orion, which goes through the constellation Monoceros and through the constellation Gemini. And so that all that white stuff you see in the picture is some of its camera noise, but it's also the winter Milky Way. And we continue the Milky Way here. About here, it makes a nice little arch over in the west. And I've rotated the next picture to be oriented toward the natural horizon. And Orion and Taurus are down here. These 2 stars up high are Castor and Pollux of Gemini. And that would put M35, open star cluster, a very nice object to show at star parties, still high in the evening sky. And the winter Milky Way goes to our right, toward Auriga, the charioteer, where also you still have a nice view of the open star clusters M37, 36, and 38 in the constellation Auriga. And you continue farther past Taurus, it puts you in the constellation Perseus, which is now flopped over on his back at this time of year. And the winter Milky Way continues to Cassiopeia, which you can barely see in this picture because it's very low and off to the edge of my camera. But those bright stars in the far corner are Cassiopeia. And next, so the winter Milky Way, if you get out to a dark site, you may see it make a nice arch over the western sky for you. Now, if you continue looking this way, as I did, next picture of my camera, you may catch Ursa Major upside down. That is the Dipper upside down, metaphorically dumping its water on us as a gesture of spring, a symbol of spring. But it's the constellation Ursa Major, the bear. And if you can see that, it makes it a very good time to check out a number of galaxies and a planetary nebula in Ursa Major. And here's some images I've taken with my 3-inch telescope. I usually set up my 8-inch Schmidt-Cassegrain on a Losmandy mount and my 3-inch telescope, and I do most of my photos with the 3-inch, and really just a lot of them just from the city. One of the things I enjoy most is not trying to get the best picture, just see what I can detect with my 3-inch telescope. But anyway, here's the Owl Nebula M97 and the galaxy M108 in Ursa Major. And here is M82 and M81, also with my 3-inch refractor taken from my backyard in Wildemar. And so anyway, we continue our scan of the sky. If we follow the arc of the handle of the Big Dipper, we come down to Arcturus, which means the constellation Boötes is rising in the east, and the constellation Virgo is also, I believe, in that picture. I didn't label the stars in it. And go a little farther from Virgo, turning my camera now toward the southeast, you will see Corvus rising. And Corvus is a distinct group of flattened foursome of stars. And my camera is now, since it's on an equatorial mount, it's all kind of twisted cattywampus, 45 degrees to the horizon. And so if you could just rotate the picture in your mind, you can imagine that straight down from Corvus, as drawn here, is that horizon. And if there just happens to be a city out there from where I took this picture. But if you're out in the desert and you can see Corvus, about midnight, that constellation will get as high as it's ever going to get from our point of view. And that will make it possible to see the globular cluster Omega Centauri. And so Omega Centauri will be right below Corvus about midnight, as high as it's going to get from the horizon. And this is a view in my 3-inch refractor. So it's a good binocular object as well as a small telescope object. And then I stopped at the area south and east of Ursa, of Canis Major, which is kind of a new area for me to look at. And so looking just a little bit this way, I'm turning my camera back to that part of the sky. And so I realized that right now, and in this next month and in the next 2 weeks, this particular part of sky is going to be as high as it's going to get in the evening. And so it's a very good chance to explore what's there before it sets for the year. And so here's a Canis Major to the right. And here is the constellation Puppis, which means the poop deck of a ship. I don't know how it's supposed to be drawn or imagined, but I drew in a few lines I traced from one of my star charts. And then over here is Vela the Sails. And apparently this was one big constellation at one time, I believe, called the Argonaut or Argos or something like that. But they split it up into separate constellations. But one of my things that I like to enjoy to find most is planetary nebula, because with my method of just taking my 3-inch scope, putting it on an area of sky, letting the image soak for a few minutes, the planetary nebula really pop as green stars, and sometimes you see more features. So I was really excited when I was trying to see what was in this picture that I'd taken by comparing my picture to my star charts, that there are a number of planetary nebula out there. And 4 of them I've never looked at or tried to photograph, but 2 of them that are higher in this picture I captured last winter for the first time using my 8-inch telescope. So here's NGC 2440. And right there in the middle, that little fuzzy thing. And then also here is this with the same setup. Here's NGC 2452, which looks like a dual lobed object. So I'm eager to get back out in the sky and to try to get pictures of the rest of them, and as well as better pictures of the 2 that I've captured already. And by the way, a word of warning, these PK numbers refer to a catalog of a list of planetary nebula. And so far, I haven't been able to photograph any of them. And so they're really faint. And so wish you luck with that. I hope to capture one finally. But also in that area, there are numerous star clusters, because this area is also the area I was describing earlier as where you see the winter Milky Way. So it should be no surprise that there are numerous star clusters in that area to look at. And a lot of these look like they'd be very easy to see in binoculars and would show up really nice in a small telescope. High overhead, this time of year is actually noted for the Leo the Lion region. And Leo the Lion, which would be rising high in the east, has numerous galaxy clusters around it, and also has the constellation Cancer, the crab, which is a great binocular object, and another good binocular object, the constellation Coma Berenices. And near Coma Berenices is like this whole area of galaxies, of faint galaxies that I've only begun to explore. And that's why one of the reasons I find, in addition to that last scene I was showing you about Vela and Puppis, this area of near Leo and Virgo and Coma Berenices is just an area that I'm very eager to get ever finer, higher magnification images of, to get pictures of. But Leo, if you draw a line, okay, Leo, view the constellation this way. There's also a carbon star in Leo. I'm quite fascinated with carbon stars, also very red, beautiful stars. And so there's one by the front paw of Leo. And if you draw a line between Regulus and the nebula, you'll come close to other galaxies, such as M66 and 65 and 105, 96 and M95. And also, if you're a Star Trek fan and are aware of the epic battle between the Borg and the Federation that took place at Wolf 359, that appears to be in this area of the sky. Just a good fact to know. But here's a few pictures I've taken, I believe, from my backyard with my 3-inch refractor of the M65 and 66 area. And this particular galaxy is one that looks very interesting to dig in a little deeper. Then here's the M95, 96, and 105 group too, also with the same equipment. And this are some pictures where I think I took all these from my backyard, again, on a particularly dark night, where I would just take my 3-inch telescope and point it at some of those galaxy clusters off the back end of Leo. And I went through later and labeled all the different galaxies I could find. This is just something I find really exciting. You can do this with a simple camera. You can do this with a 50mm lens camera, or you can do it with a small telescope, just photograph an area, even for a minute. And then when you get it into Photoshop or something like that, you can amp up the exposure and just see what you can detect. And I just find it really fun, especially a great thing to do on a rainy day. And so here's another area around M100, numerous galaxies. They just keep showing up the longer you let your camera soak in one of these areas. And then here's the last little area that I'm going to show you tonight around M99. And what started for me 20 years ago as an intimidating area of the sky now is just overwhelming, which is also intimidating, but I'm very eager to get out there. And I hope all of that whets your appetite to do the same. So thank you.
Thank you, John, for yet another great presentation. I enjoyed it thoroughly. Hi, my name is Reza, and I'm the Vice President of the club. I, too, would like to welcome you to the April 8th, 2022 General Meeting of the Orange County Astronomers. Our speaker at this meeting earned his PhD in astrophysics from the University of Florida in 2006, but left a promising research career in cosmology to focus on science communication full-time. He has authored several popular science books and runs a blog called Starts with a Bang, for which he has won numerous awards. Please join me in welcoming Dr. Ethan Siegel. Ethan. Ethan, we are all ready for you. Let me help you unmute.
Yeah, sorry.
So the floor is yours, and we're all eyes and ears.
Right. Hi, everyone. All right, let's see if I can. I know we practiced this, so I am going to get my screen sharing over here. Give me just a sec. Zoom, zoom, zoom. I know you're there. All right, let's see if we can get it. I'm going to make this happen. So, oh, no, that's the wrong window. I'm assuming everyone can see my whole
Right.
controls and everything. All right, let's try that again. How about this? Does that look? Oh, that's closer. All right, let's start at the beginning. All right, hi, everybody. It's my pleasure to join you. Thanks for inviting me, Reza. John, I really enjoyed your presentation. It made me remember, you know, when you show M81 and M82, those are very, very special galaxies to me because they are the first galaxies I ever saw for myself through like my own astronomical equipment. I know there are a lot of ways to do amateur astronomy, and I actually love using a pair of tripod mounted binoculars. There for me is nothing like getting those wide field views of the sky and seeing all the wonderful stuff that's out there. And M81 was the first galaxy I ever found for myself on my own with my astronomy binoculars. And I was shocked that as soon as I found M81, there was M82 right next to it. That in that same field of view, there it was. I felt like I got my first two for the price of one, and that was very cool. And every time I see amateur astronomers talk about those galaxies, it brings me back to that time where I first saw it myself. And I'm sure you're all full of you know, stories where you felt just like that. So I'm here to talk to you today about the end of the beginning, because most of us have heard about the Big Bang, and most of us have had this idea in our heads that the universe began from, you know, if you go back and back and back, it was hotter, it was denser, it was more uniform, and you can go all the way back to a singularity, and that is the birth of space and time. And I am here to tell you that last part of going back to a singularity, and that's the birth of space and time, has not been the case scientifically for more than 40 years. And most people don't know this, and I want you to know all of this. So that is what I'm here to talk to you about today. So the way we're going to do this is I'm going to start by talking about relativity and the expanding universe, why the Big Bang was such a big idea, and then what we observe, what agrees with the Big Bang and what breaks down about the Big Bang. And then we're going to talk about the puzzles and problems associated with the Big Bang and a new theory that came along. Basically, it started in December of 1979. And that new theory is called cosmic inflation. And that is something that offered new predictions that we could go out, look for, and see how did it stack up against the Big Bang without inflation. And that's where we're going to wind up. So let's start off by talking about space-time. Back in the day of Newton, right, he had this idea that gravitation was universal, that every mass in the universe attracted every other mass in the universe. And all you had to do, if you wanted to know how any system of masses would evolve into the future, is you just had to give him the positions, the momentum, and the masses of every mass in the universe. You do that, he writes it down, he calculates the forces between them, and if you had arbitrarily large computational power, you could just calculate how everything would evolve going forward, and you would have this beautiful deterministic universe where everything acted on everything else instantaneously. Then Einstein came along and we realized that was not possible, because this idea of instantaneously is not the same for you as it is for me. It's not the same for any observers, because people move at different speeds and they have different views of what distance mean, and they have different rates of time at which their clocks pass. So you can't just say, oh, time is absolute and these things happen instantaneously. You have to say, oh, okay, well, it looks like I have to go way back and come up with a whole new theory, especially if I want to account for gravity. Because special relativity, which talked about rates and distances in time and motion, was only in a universe without gravity. You put gravity in there and you say, oh no, this is incompatible too. So Einstein, it took him 10 years and lots of collaborators to turn special relativity and this idea of gravitation into general relativity. So instead of having this sort of absolute space that everyone agreed on and everyone understood, and this absolute time for which he calculated everything, he said, no. Space-time is this four-dimensional interwoven manifold. It's like a fabric. And the way it works is mass, matter, energy, all forms of energy, they cause space-time to curve. And then that curved space-time tells matter and energy how to move through it. And that's the big idea. That's where space-time came from. Einstein said, space-time is like the stage where the play of the universe takes place. And all the particles and masses and quanta of energy and photons, everything is a performer on that stage. So the matter and energy tells the space-time how to curve, and then that curved space-time tells matter and energy how to move. And this was fascinating immediately, because when we looked out at the universe, what do we see? Well, back in Einstein's day, they looked out at the universe and they saw stuff in all directions. Most of it was stars within the Milky Way. We didn't yet know that there were galaxies outside of the Milky Way. We didn't know what those spirals and ellipticals in the sky were, but they knew there was stuff everywhere. This on its own is a problem. It's a worse problem when you know how big and how full of stuff the universe actually is. So if we had discovered this today, if we had discovered this after knowing how big the universe was, we would have had like even bigger problem of this. If you have a universe full of matter, you say, oh, it curves space here, it curves space there. Everywhere you have matter, space is curved. So if you have matter everywhere, does that mean there's an overall curvature to space, right? It's like if you had a uniform distribution of matter everywhere throughout space-time, wouldn't the whole thing be curved? And the answer, because you can calculate that, is, oh, yes. In fact, if you have a universe that's evenly distributed with mass, and you said, okay, I'm going to distribute it whatever shape I want, pyramid, sphere, cube, potato, anything you want, guess what? It always inevitably collapses down to a spherical black hole. This is an unstable universe. It's unstable against gravitational collapse. So how do you fix this? Obviously, you don't want your universe to collapse, and our universe hasn't already collapsed. So how do you work around that in general relativity? Well, in Newton's gravitation, it turns out you also cannot have a static solution. You can have multiple things orbit each other, although there is this problem of chaos where if you have more than two things orbiting each other, the mutual gravitational effects will inevitably kick everything out until you're down to two, but that takes long times. With Einstein, no, you can't do it. You are going to gravitationally collapse. So he said, aha, I'm going to put an extra ingredient in. I can put this uniform amount of energy inherent to space itself. That's what I call a cosmological constant, and I can tune it so that it holds the universe up against gravitational collapse. If you had evenly distributed masses everywhere and a perfectly tuned cosmological constant, it could balance that gravitational collapse and leave you with a static universe. Okay, and then you say, okay, well, what happens if I take one atom in your perfect even distribution and I just nudge it a tiny, tiny bit, just perturb it away from that perfect equilibrium? it is like starting off the ultimate chain of gravity dominoes, because you knock that first one, and in short order, gravity is a nonlinear runaway process. It all leads to, oh, we've got an overdensity here and an underdensity here, and the overdensity is going to grow and the underdensity is going to shrink and give up its matter. And before you know it, you have a region where everything collapses and you form a giant spherical black hole and it sucks everything else in. And in this region, it expands away and you lose all the stuff and it helps grow the black hole. That's bad. How can you prevent a gravitationally unstable universe from destroying itself? Well, first solution to do that was De Sitter, who said, hey, Einstein, guess what? If this cosmological constant is big enough, it will cause the universe to expand, and gravitational collapse can't destroy your universe. Alexander Friedman in 1922 went and derived, hey, guess what? If you have this unstable universe, then it must either be expanding or contracting. So in theory, you should be able to go out and measure these distant objects and see, are they expanding and moving away from you, or are they contracting and moving towards you? And that will tell you what the universe is. Friedman unfortunately died young, but this idea was picked up by others because there were two big key observations that happened. One was from Edwin Hubble, and one was from Vesto Slipher. And these two names are not equally well known, and I think they should be. Because Edwin Hubble did this very famous thing. He was looking at the big Andromeda Nebula. He had his new 100-inch telescope, the most powerful, biggest telescope in the world at the time. He got in on the ground floor in 1917, and in 1923, he was looking at the Great Nebula in Andromeda. We did not know it was a galaxy yet. So he's out there looking at this nebula, and what does he see? Oh, well, I see, it looks like this big diffuse thing on my plate, and I'm watching it, and what do I see? I'm watching it on October 6, 1923, and I see in one area of the sky, there's this little tiny point of light that flares up and gets brighter over a few days, and then it fades away. And Hubble goes, ooh, how exciting, a nova. And so he catalogs it with an N, and he sees a second nova, and he sees a third nova. And this is over the course of a few nights. And then he sees a fourth nova, right? Big deal. No, it is a big deal because that fourth nova is in the same exact place as the first one. And if you know what a nova is, where mass accretes on the surface of a white dwarf until you have enough of it that nuclear fusion ignites on the surface and you get this big flare up, you know that in most cases, it takes thousands of years for a nova to recharge. In a few cases, it'll take only centuries or decades. And I think the fastest one is like 7 years. Okay, but 4 nights, 4 nights is nuts. That does not happen. Hubble, in Hubble fashion, defaces the photographic plate, and instead of marking it with an N, takes his red pen, crosses it out, writes VAR exclamation point, because that, he knows, has to be a variable star. And since we know from the work of Henrietta Leavitt that there is a relationship between the period of a variable star and how intrinsically bright it is, all of a sudden, Hubble can tell you how far away this object is. Because if you know how brightness spreads out with distance, and it does, it just spreads out like a spherical shell, then you can say, oh, I know how intrinsically bright it is, and I can measure how apparently bright it is, and just from that, I know how far away it is. And even though Hubble lowballed the distance by quite a bit, he still found it was about 900,000 light years away. In reality, Andromeda is like 2.5 million light years away. But for comparison, everything else that was in the Milky Way was within a few thousand light years at most. So this thing had to be outside of our own galaxy. And if you combine this with Vesto Slipher's observations, where he said, hey, I can look at this nebula And look what I see. I see it has an intrinsic redshift, like it's moving away from us. And the fainter and more compact and possibly far away these nebulae are, the greater the redshift is associated with them. So you can see these different speeds, and the different shift to the line indicates that these things appear to be moving away from us. So what's going on? You have these spiral nebulae, they recede very fast. They must be outside our galaxy because we know, even with Newton and Einstein, how gravitation works. And you can see from these apparent recession speeds, these are way faster than the escape velocity from our galaxy. So they've got to be both far away and moving fast away from us. This was the breakthrough. Hubble observed the Cepheids, observed these variable stars, computed the distance to these objects, took the data from Vesto Slipher's work about how fast are they moving away from us, and he just plotted it. He just plotted speed, recession speed versus distance. And what did you get? You got a nice straight line, right? He got a different slope, he got a different, but that doesn't matter. What matters is this is how we did it back in the 1920s, and it's still how we do it today. And this is how you discover Hubble's law, that the farther away an object is, the faster it appears to recede from you, and the greater its redshift is. Why? Because the universe is expanding. I always love the analogies of either, if you're okay with thinking two-dimensionally, to think about the surface of a balloon with coins glued on it. If you're not okay with thinking two-dimensionally, if you get obsessed about what's happening inside the balloon, think about instead a leavening loaf of raisin bread. You have raisins all throughout it, and the raisins are like the galaxies, and the dough is like the space. So you have to imagine invisible dough. But the dough leavens, and the raisins all expand away from each other. Or you blow the balloon up and the coins all expand away from each other. And the farther away one coin appears to be from the other, or one raisin appears to be from the other, the more the space in between them is going to stretch. And what that means is that if one of these galaxies emits light, then as that light gets emitted and travels through the universe and the universe expands, the wavelength of that light, which determines what its energy is going to get stretched to longer and longer wavelengths. And longer wavelengths are redder wavelengths. And that's why we see a redshift, and it's more redshifted the farther away it is. So if the universe is expanding and it's cooling, then what happens if we think into the past? Well, in the past, that means it had to be hotter, it had to be denser, it had to be, if it's been gravitating and clumping, it had to be more uniform. So that basically is the start of the idea of the Big Bang. The details tell you, oh, it's volume. So as your size increases, the volume of space that contains your observable universe increases as the cube of the size of the universe. The photons have an energy, and in addition to getting diluted, because as your universe expands, their density goes down, they also get stretched. So they lose energy, they lose it by another factor of this 1 over distance. So in the past, the radius of the observable universe was smaller, the temperature was hotter, and everything was more uniform at earlier times as well. So let's think back in time. If we have our universe today, what happens when we go back? If we think back in time, well, we say galaxies had to grow and evolve because over time, they're going to draw in matter from intergalactic space. They're going to pull on each other and merge together, and we see galaxy mergers happen. And that tells us that the population of galaxies we see today should be different than the populations of galaxies we see when we look further away, because the farther away we look, the farther back in time we're looking, because the galaxies that we're seeing far away, we're seeing them as they were younger. If a galaxy is far enough away that it takes 1 billion years for light to go from it to our eyes, then we're seeing it as it was 1 billion years ago. In fact, just last week, they announced we found the farthest galaxy ever. We have to look back 13.5 billion years to get the light from this galaxy, which means it's as it was just 300 million years after the start of the Big Bang. Younger galaxies, therefore, if they grow over time, they should be smaller in size. They should be less evolved in their shape. They should be bluer in color. Why? Because when you form stars, you form them of all different colors. And the hottest ones, the bluest ones, will burn through their fuel the fastest and die first. So if you form a whole bunch of stars, you're going to see it's dominated by the blue ones. But as you wait, the blue ones die, and then the next blue ones, and then the white ones, and then the yellow ones. And so things get redder as time goes on, and they're bluer earlier. And finally, they're going to have different luminosity functions because it takes stars to make heavy elements. And heavy elements determine how your clouds of gas that form stars cool. So if you are less good at cooling down because you have fewer heavy elements, then that means, oh, I'm going to need bigger clumps of matter to form my stars, and therefore I'm going to have heavier stars early on, and I'm only going to have the possibility of lighter stars as things get older. So what do we actually see? Well, this is exactly what we see. If we correct for the cosmological redshift, we see that galaxies that are similar to today's Milky Way in properties actually are smaller, have less evolved morphologies, and are intrinsically bluer and are greater in density as you go back in time. And you expect them to be greater in density, one, because they haven't merged together as much, and two, because the universe was smaller in the past. So you expect to see galaxies more closely clustered together, and we do. But what happened if I wanted to go back before this? If I wanted to say, yeah, I'm looking billions of years ago, but what if I look far enough? Well, you say, hey, if you could continue back in time, you would find a time before there were stars. If things were uniform enough, maybe there's a time when there weren't any stars. So we should have a dark ages in our universe. You can say, hey, if you had a time before there were stars, well, guess what? Starlight is what it takes to ionize neutral atoms. So if we had neutral atoms in the universe, you need to form stars to make the universe ionized. If it's not, hey, guess what? You look at the Milky Way, you see those dark bands across the Milky Way? Those are neutral atoms. Neutral atoms block starlight. So if you want to see stars, you had better ionize all those neutral atoms so you can see them. I wonder then, if you look back early enough in the universe, if you look back far and far enough, will you find gas clouds that make like a wall that block light beyond a certain point? And the answer is yes, you do. We have something that we've measured called the Gunn-Peterson trough, where basically if you have a galaxy that's farther away than about, if you account for the expanding universe, farther away than about 30 billion light years, which corresponds to a redshift of about 6. So if you see things with a redshift that's greater than 6, there is this wall of neutral matter in front of them, this wall of neutral hydrogen atoms. And we call that the Gunn-Peterson trough because we see it, boom, it wipes out all these features in the absorption lines of quasars because it just absorbs all the matter. So the universe was at one point opaque to matter. And what we have actually found is some of those clouds of gas we can measure them and find they are pristine. They only have hydrogen and helium in them. They have no heavier elements, which tells us they've never formed stars. They found these for the first time in 2011, and as of today, I am aware of 3 clouds of gas. Wow, 3. But 3 is huge. If you see 1, you might be like, yeah, maybe that's the only one. But if you see 2 or more, you know there are plenty. So this is something that I think James Webb and ALMA combined will be exquisite at finding. So I'm looking forward to that. All right, so we find that the universe was opaque, and we find that some gas clouds will be pristine, but can we go even back further? And the answer is yes. We can imagine that if we had this radiation, right, and the universe was smaller, then it was hotter. And if it was smaller, then it was hotter. And at some point, it gets so hot that you can't make neutral atoms, because anytime you have an electron binding to your atomic nucleus, a high enough energy photon is going to come along, smack the electron, kick it off, and boom, that's it. Sorry, folks, your atom is ionized and you have an ion instead of an atom. So that means that we should have in the early universe a universe that expands, cools, and for the first time will form neutral atoms. And when it does, finally, those photons that were bouncing around mostly off of the free electrons, these are low energy photons now. It expands and cools, and most of them are not visible light photons, but infrared photons. By the way, if you had infrared eyes, you wouldn't see those dark bands in the Milky Way. Those dark bands are made of dust, and dust grains have a particular size. The size is the size is bigger than the wavelength of visible light. So they absorb visible light, but the size is smaller than infrared light. So infrared light passes through that, just like visible light passes through the little holes on your microwave door, while the microwaves bounce off of it and stay inside and heat up your food. So that's what we should say is, ooh, we should be able to see this leftover bath of radiation that was emitted from this transition from the universe was full of ions to the universe has neutral atoms in it, right? Because early on, if I look at number 1, what happens, right? Panel 1, I have nuclei, I have electrons, and I have photons, and they all smack together. Every once in a while, if I come to 2A, I have a proton and an electron, and they'll, bam, make a hydrogen atom, but they'll emit a photon. And that photon they emit will find another neutral hydrogen atom, and bam, we'll ionize it again. So, oh no, I made an atom, and it just went and destroyed another atom that I had made. So how do I ever make a neutral universe? The answer is there's a special quantum transition, where if I look at 2B, I can have a proton and an electron, bam, bind together, but instead of emitting 1 photon, they emit 2 lower energy photons. And now that can't reionize the atom. So that's how I wind up with panel 3, a neutral universe. And then based on that, I would make predictions that, hey, I should see, even though the universe has expanded and cooled, that radiation should still be there in all directions at some very low temperature. And bam, there it is. Discovered 1964-65 by Arno Penzias and Robert Wilson using the Horn antenna in Holmdel, New Jersey. Found it by mistake, didn't know what they saw. Notice there was the Milky Way in there. You can see the Milky Way that emits its own signals. They tried everything. They tried pointing their antenna at the ground and then back up, and that radiation was still there. They tried turning it off and turning it on again. They tried giving it a deep clean because there were pigeons living in there. So they, as far as I know, are the only Nobel Prize winners to clean bird shit out of their equipment as part of their Nobel Prize winning research. And yet they did it. And guess what? It's still there because it's of cosmic origin. This is a black body. It is the most perfect black body known in the entire universe. The cosmic microwave background, I'm going to show you some slides here. We measured it was perfectly uniform, except for our motion through it to 1 part in about 30,000. It was only with the launch of the COBE satellite in 1992 that we could detect those first primordial imperfections. And then with WMAP in the 2000s and Planck in the 2010s, we were able to get better and better resolution and measure these temperature fluctuations exquisitely. And there's a lot of detail in there that teaches us about our universe, which is important. This curve on the right that says intensity versus frequency, that is a perfect black body curve. The line is if you calculate a perfect black body. The data points you see are the COBE data with 400 sigma error bars. Normally we graph things with 1 or 2 or 3 sigma error bars. These are 400 sigma error bars, just to give you an illustration of how perfect of a black body the cosmic microwave background is. I am not joking, most perfect black body in history. The sun, by the way, is a lousy black body because it emits light not from a solid surface, but from a series of surfaces that really make up its photosphere. So the sun is actually the sum of a number of black bodies at many different temperatures and is not well fit by a black body. Every once in a while, someone will ask me, well, how do you know that's cosmic? And how do you know it's not reflected starlight, reflected off of some fog? And the answer is that starlight doesn't have a black body spectrum. This does. And that's how you know. So you can say, all right, so big deal. You can make neutral atoms and see that leftover signal. What else can you do if you go back further and you say, okay, well, let me go back when things are so hot that I can't even make an atomic nucleus. If I had a proton and a neutron, simplest things, right? Raw proton, raw neutron, smack them together, make a deuteron. Wrong, because if it's hot enough, a photon will come along and smash them apart. And this is actually a problem because in the early universe, deuterium, that first step to building all the other heavy elements, is extremely fragile. If you get a photon of, only a few billion Kelvin, it's gonna break them apart. And that's tough because you want to make nuclear fusion. You want to build up elements. You protons and neutrons, hot, dense, early universe. You're like, hey, it's like the inside of a star over there. Well, too bad. You have to wait until the universe cools and expands enough that its density is only 1/1 billionth what it is in the sun. So by time you can actually form stable deuterium and start this chain reaction to build up helium-3 and tritium and helium-4, and by time you get there, it turns out that, guess what? The universe is already pretty cool and you're not making a whole lot that's heavier. So you say, okay, look, here's what I can do is based on the density of matter, the density of particles compared to the density of photons, I can calculate how much do I expect the ratio of these light elements to be compared to how much plain old hydrogen is left. How much deuterium do I get? How much helium-3 do I get? How much lithium-7 do I get? And we can actually observe that because when starlight from quasars passes through clouds of matter, we can take the most pristine ones and say how much hydrogen is in there, how much deuterium is in there. And we can look at the less and less pristine ones, the more processed ones, and use that to extrapolate back to perfectly pristine environments. Everything agrees with one consistent number, and that's exactly what we want. We have measured the baryon to photon density in the universe very precisely. About for every 10 billion photons that there are about 6 protons in the universe, and that is something we have measured. Fun fact. So that's enough that I would say that we can confirm the Big Bang, but why stop here? We can go back farther. We can say, look, I can imagine a time where it was so hot that things would smack together and they would spontaneously produce pairs of matter and antimatter. That's how we make antimatter, is you smash 2 things together and extra energy and you say equals mc squared and you get matter antimatter pairs that pop out. So we know, okay, I can do this, but somehow our universe made more matter than antimatter, because everywhere we look, stars, galaxies, galaxy clusters, the cosmic web, we don't see these copious amounts of matter-antimatter annihilation. We know that every star and every galaxy in the observable universe is made of matter and not antimatter. So, why did that happen? We know that you can go back further and you can say, ooh, at some point I couldn't have even made protons and neutrons because things would have been so hot and dense that I would actually have a quark gluon plasma. I can go back even further and imagine, okay, what happens at these super high energies? Do I have grand unified theories? Does the proton decay? Will I get leptoquarks out? Do the couplings run and unify? Will there be relic particles like magnetic monopoles left over? And finally, you say, I can go all the way back to the singularity, and bam, there you have it. That's my original idea of the Big Bang. What would that mean? What would it mean if my universe began from a singularity? It means I would have infinite densities at that moment. It means that space would be compressed down to an infinitesimally small scale, and that I would be working on infinitesimally small time scales. I would have to extrapolate to arbitrarily high energies and temperatures. I would have to imagine that this was the birth of all space, time, matter, and energy, and maybe even the laws of physics. George Gamow is often credited as being the father of the Big Bang, and he called this a day without a yesterday, which is very, very beautiful and poetic. So it's reasonable to think this, right? But there are problems with this. One, our laws of physics break down before you reach infinite energies, before you reach infinitesimally small time or distance scales. You worry about what's going to happen if my universe is so small that a quantum fluctuation that I can't prevent because Heisenberg's uncertainty principle is baked into our reality. What happens when a quantum fluctuation must make a black hole because it's so energetic? Oh, that seems like a problem. What happens when my calculations fail me? Well, this is why there are kind of two definitions for the Big Bang. In the old days, you would say the Big Bang is all of this, right? It is the singular beginning, and it is the hot, dense state full of matter and energy, and it is the early stages of the universe and how it all unfolds. But we don't have evidence for the singular beginning part. We only have evidence for basically what happens at nuclear energy scales and below. There's a limit to what we can extrapolate back to and still actually check that. Plus, if you do go back to a singularity, if you imagine this Big Bang picture, what do you think about? It actually raises some unexplained puzzles. For one, there's what I call a horizon problem. If I look in this direction or that direction or that direction in the universe, I know the places I'm seeing didn't have enough time since the Big Bang because signals are limited by the speed of light and the universe is expanding. They didn't have enough time to talk to each other. They didn't have enough time to exchange information. And just like you'd kind of wonder if you had a space heater in the corner of your room and you turned it on and 5 seconds later, every single part of your room raised by the same temperature, you would say that shouldn't happen. It should take time for the heat to propagate, for the signal to propagate, and it shouldn't be even. But somehow the universe knows to be the exact same temperature. I showed you the black body graph everywhere. Why is that? That's what we call the horizon problem. It's a property that the Big Bang doesn't explain. We also have the isotropy problem. Isotropic means the same in all directions. Why does the large-scale structure of the universe look the same in all directions? It's almost like our universe was born planted with the same types of seeds everywhere. Where did those seeds come from? Because those seeds are required to lead to the growth formation of structure. The large scale structure is the same in all directions. Why is this? No explanation in the Big Bang. There's also something physicists call the monopole problem. Pretty much every extrapolation that you can make in theoretical physics up to very high energy scales is going to produce magnetic monopoles. This was proven by Gerard Tekout and a Soviet physicist named Polyakov. And so you say, hey, if you reach these ultra high temperatures, why are there no relics from this ultra high temperature time? There should be magnetic monopoles, there should be other exotic relics, and yet we don't see any of them. So why not? Why don't we see any of these new particles that we expect should occur at these higher energy scales? There's also what I call the flatness problem. Other people call it that too, it's not just me. Why is the spatial curvature of the universe so perfectly close to zero? Why is there not large positive or negative curvature? According to the Big Bang, the universe is a race between the initial expansion and the gravitation of everything in it that works to pull it back together. And you can imagine, oh, maybe there's enough stuff in the universe that gravitation wins. Whatever the initial expansion was, gravitation slows it down. Finally, it reaches a maximum size and gravitation recollapses it. Bam, perfect. Or you can say, oh, what if it's the other way? What if it expands, 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 and gravity tries to pull it back together, but can't? And the expansion wins and it runs away forever. Or you can play the Goldilocks and the Three Bears game. What if the universe is just right? What if the universe expands and slows down, expands and slows down, and asymptotes approaches expanding at zero? It approaches no expansion, but never quite gets there, right? Asymptotes, for those of you who just recently graduated college, are kind of like your student loans. You think you're going to pay them off, but it also feels like you'll never get down to a balance of zero, right? So that's kind of what you can imagine happen. It turns out that Goldilocks case corresponds to a perfectly flat universe. A universe that recollapses is a closed universe. A universe that expands forever is an open universe. And yet when we look out, we see it's perfectly flat. So why is there that perfect balance? And finally, I'll give you one more problem. There's what I call the small fluctuation problems. When I said, let me see if I can pull you back to here. This is the uniform universe. This part, the imperfections in the universe, these imperfections happen at the 1 part in 30,000 level. Why are these fluctuations so small? If the universe got heated up to arbitrarily high energies, you would expect fluctuations in temperature from one region to the other to be of order 1, not of order 1 over 30,000. So why are the temperature fluctuations not at very high energies? None of these have explanations in the Big Bang. You either have to play Lady Gaga and say the universe was born this way, or I don't like that. I do like Lady Gaga, but I don't like that explanation. Why? Because to me, that gives up on science. Science, what you do is you say, okay, if I have these things without an explanation, what I'm going to try to do is come up with a plausible explanation. And then I'm going to do this thing. I'm going to come up with the plausible explanation, and I'm going to test for 3 things. First thing, whatever the successes of my old model were, my new model had better reproduce every single one. I'd better be able to recover all of the predictions of the old theory from my new one. Number 2, I'd better explain some of the things that the old theory couldn't explain. I have to do better than the old one. I have to succeed where the old theory didn't succeed. And then number 3, so if anyone is like, Ethan, what about Roger Penrose's idea where he says that we have a conformal cyclic cosmology? I said, no, you have to meet criteria number 3, which means you have to make new predictions that differ from the old theory's predictions that you can go out and test one against the other and determine which one the evidence favors. You have to do all three, otherwise you don't get to overthrow the theory. That's what it takes. So in 1979, by the way, all 5 of these problems I just talked about were a favorite of Bob Dicke. Bob Dicke would give Einstein Day lectures and he would talk about the problems with the Big Bang. Bob Dicke was the physicist who got scooped by Penzias and Wilson. They were building a device called a Dicke radiometer to go detect this afterglow of the Big Bang, which they called the primeval fireball back in the day. Such a better name than the cosmic microwave background. But they got scooped. And so Dicke was giving his Einstein Day lectures, and in the audience was a young postdoc, now MIT professor named Alan Guth. And these are Alan Guth's notes from Bob Dicke's Einstein Day lectures. Spectacular realization. This kind of supercooling, he is imagining, hey, guess what? What if I had a universe that didn't expand like it had matter in it, or didn't expand like it had radiation in it, but rather had energy inherent to the fabric of space itself? What if it just whooshed and expanded relentlessly and exponentially instead? What if, instead of expanding and cooling and having your density drop, what if your energy density remained constant? Then as a certain amount of time passed, you'd double in size. And as that same amount of time passed in all 3 dimensions, you would double, double, double in size. And then as that same amount of time passed again doubled. It means that after 100 of these time steps pass, you will have gone from a scale smaller than the Planck subatomic scale to a scale larger than the observable universe. Doubling things in short order gets really large really fast. And if you don't believe me, take someone dear to you and offer to give them 1 cent on the first of the month. And then on the second of the month, you will give them 2 cents. And then on the third of the month, you will give them 4 cents. And so on. Keep doubling. You will discover by the end of the month that you are required to give them more money than exists on planet Earth. And you will not be very happy that you decided to do that experiment. So what is cosmic inflation if we have space expanding like this? It's a period prior to the hot, dense, expanding state that the Big Bang describes, because it imagines that the universe doesn't have matter or radiation or quanta in it of any kind. Instead, space expands exponentially during this time. And exponential can be fast or slow, but its big property is it's relentless. So in about 10 to the minus 32, 10 to the minus 33 seconds, you can turn a Planck scale region into something that's bigger than the size of the observable universe is today. It will also take whatever shape the universe was and stretch it so it's indistinguishable from flat, right? I could have had this saddle-like curved universe or this circle-like curved universe. And if I expanded it so big, expand, it would look flat to you. Just like if I said, hey, go outside, go to your backyard and try to measure the curvature of the Earth. You would say, no, my backyard is too small. I can't measure that the Earth is curved on the scale of my backyard. And you are correct. So how does inflation solve the Big Bang's problems? Well, here on the left, I can imagine I had a tiny region of space where everything had the same properties because everything was at the same spot. And then whoosh, I expanded it exponentially. It grew to be huge. Well, now I have an explanation for why it's the same temperature everywhere. I solved the horizon problem because it was all in one location in the past. Things did have time to talk to each other way back when, but then it just expanded so fast that the parts I'm seeing here, there, everywhere, they're all imprinted from the past when they were together. That's why they have the same properties today, not because they talk to each other at late times, but at early times. They were connected before and they still have the memory of what they were doing back then. Why, over on the right, don't I have these leftover high energy relics, magnetic monopoles and what have you? It's because even if they existed, even if I had a universe that was full of them, by the nature of inflation, I exponentially expand things away. So now, bip, 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 at most in my universe, I'm going to have one magnetic monopole in my whole universe. So don't be surprised you don't see them. Your odds are not very good. And finally, it solves the problem down here at the bottom of why does the universe look flat? And it's because, oh, well, it expanded and expanded and expanded and expanded. And no matter how big or small I am over here on the right side of the bottom image, it's going to look flat. If it expands enough, it's just going to look flat. So how does inflation work? I like to think of inflation as you have a plateau. Bam, here I am. I'm on top of my plateau, and the plateau is really flat. And as long as I'm up high here, all of my energy is inherent to the fabric of space, and it expands exponentially. And if I got a nice flat plateau up here, I'll only roll slowly. And so as long as I'm rolling slowly, inflation, 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 inflation. But at some point, I reach the end of the plateau. And that means I start to roll into the valley and I oscillate down here. And when that happens, there's one more thing that happens. Now I've taken my energy that was inherent to space and whew, I'm losing it. I've gone down the hill. What's happening is this is the end of inflation. The energy that was inherent to space that drove inflation now gets converted into matter and radiation. It's sort of like, oh, inflation was so good. It's like a little bowling ball rolling over like a game of, where you have like a bunch of cubes all packed together and the ball rolls over it. And sometimes there'll be a weak spot and the ball will struggle going over it. But at some point, the ball's going to sink through the cube. And when it does, the whole shebang comes crashing down. Inflation ends everywhere, gets converted into matter of energy, and bam, when things get converted into matter and energy, now I have a universe not dominated by energy according to space itself, but by matter and radiation, and things are going to expand just like they did here. So inflation comes before and replaces this notion of that singularity. It means there's a cutoff to how far back we go, and then we had inflation before that. So this solves the Big Bang puzzles. The universe had the same temperature because it was in causal contact in the past. The universe is the same in all directions because the imperfections that exist must have been created by the same processes everywhere. The universe, we already talked about, always has these quantum fluctuations happening on tiny, tiny subatomic scales. But if you are having inflating space that expands exponentially, they're going to get stretched across the universe. And as these fluctuations get stretched across the universe, they're going to make some regions with above average density and some regions with below average density. And they're going to give that same spectrum of seed fluctuations everywhere. There are no monopoles because the universe expanded them away during inflation. And the universe looks flat because inflation stretched it so it'd be indistinguishable from flat. And it has small fluctuations only because inflation must have occurred at an energy scale that's small compared to the Planck scale. In fact, that's been constrained now. It has to be no greater than about 1/400th of the Planck scale, which is kind of impressive. But it also makes new predictions, and this is my favorite part. It provides physical ways to observationally test, confirm, validate, or falsify inflation. It says, okay,
I can measure the scalar spectral index, which is the spectrum of seed fluctuations. Inflation predicts that we should have a scalar spectral index that is almost, but not quite 1. It means it should have just slightly bigger magnitude fluctuations on large cosmic scales than small ones. And in fact, when we go to measure that, we say, oh man, here are my scale invariant fluctuations, but when I go to measure that spectral index, I'm getting that it's about 0.96 or 0.97, different than 1. That's a crazy good prediction from inflation. Original Big Bang without inflation, no prediction at all. I could say, what else? Oh, curvature. I should constrain that my curvature is indistinguishable from 0, and it shouldn't show up until I can start measuring the 4th, 5th, 6th significant digit. Well, it's constrained right now to be less than about 0.01, but it's predicted to be between about 0.001 and 0.0001. So right now we say this is the curvature parameter. It's hanging out there pretty good to 0. This is part of the motivation for the Nancy Roman telescope, which will be NASA's next flagship mission after James Webb. One of its goals is to get enough data about the distant expanding universe to measure this better than ever. What's another one? Well, you have different types of fluctuations you can have. You can have fluctuations be adiabatic, which means they are in nature of constant entropy everywhere, or they could be isocurvature of constant curvature everywhere. Inflation's really specific about that. It says these should be 100% adiabatic and 0% isocurvature. And when we go and measure them, what we find is consistent with that. In fact, we've been able to say from our observations, at least 98.7% of them are adiabatic, and at most 1.3% of them are isocurvature. That's pretty good for this prediction. Then you say there should be fluctuations that exist on scales larger than the cosmic horizon permits. You have the expanding universe, you have the speed of light. There should be a maximum scale that you should see these fluctuations on. And yet, when we measure those details of the cosmic microwave background that show up not just in Planck, but in the Planck polarization, you can see, hey, here's the horizon. These are larger scales. Look at that. Boom. Super horizon correlations. Wow. Then you say there's a maximum reheat temperature. How hot could the universe have gotten after the end of inflation and the start of the hot Big Bang? It's more than 100 times lower than the Planck scale. So we can say, inflation generates gravitational waves. It generates these matter imperfections, and we can measure these matter imperfections and determine, oh, there was a maximum temperature that the universe could have reached, and it's this much lower than the Planck scale. And that for me is a really strong argument, because remember, if you had a singular beginning, infinite densities, arbitrarily high energies and temperatures, we can look at the universe we have and say, no, you can't get to arbitrarily high energy. You can't get to arbitrarily high temperature. The universe, as we observe it from the limits on the fluctuations in the microwave background, prohibit that. And finally, the last prediction, and this is the only one that hasn't been validated yet, inflation tells you what the spectrum of primordial gravitational waves should be. What it doesn't tell you is what the amplitude of the gravitational wave fluctuation should be. So we know that it's not like these most optimistic models, but it could be down, 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 down. We have to keep looking, because it's one of those things that we know what it should be, but we don't know how big it should be. It could be minuscule, but we have to keep looking because we know what it ought to look like, and I want to find out if it looks like that. There's one more, by the way, bonus prediction that inflation makes. And I just want to bring this up, even though you can't observe it. Inflation, when I described it to you earlier, I described it like a classical field, like a ball on a plateau that was rolling. But inflation, like all fields in the universe, should be a quantum field. What do quantum fields do? Well, they're not like single particles, they're like waves, and they spread out over time. They have an inherent uncertainty in their position. So think about this. If I have something that's rolling slowly and also spreading out slowly, there's a chance if it's rolling slowly enough, it will spread out faster than it rolls, right? If it happens to spread out towards the valley, then it's going to roll into it even more easily. But if it happens to spread out away from the valley, then it's just going to lead to more and more inflation. And this is something that we can quantify. And when you do quantify it, this is the mind-blowing thing. The more inflation you need, if you want to get enough inflation to actually solve the Big Bang puzzles that we want to solve, then the parts of the universe, the pieces of the universe that continue inflating become larger. They grow faster than the regions where inflation ends and you get a hot Big Bang. What does this lead to? It should lead to many disconnected Big Bangs occurring. If I imagine I have inflation and then wherever I get a red X, that's where inflation ends, but wherever I don't, inflation continues. You can prove that if you want to get enough inflation to explain the observed properties of the universe, then you inevitably will have inflation continue for an eternity. Once you start it, there will always be regions that inflate. And what that means is that we should have a multiverse where here I have inflating space and maybe it rolls into the valley here and I get a hot Big Bang, but all around it, I get more inflating space. And then here I have a hot Big Bang and it ends there. But these regions where I have a hot Big Bang, they get pushed away from each other at an exponential rate. No two universes within the multiverse should ever collide. So that's why I say, although this is a prediction, it's an untestable prediction. I think it's important to know what the theoretical consequences are, but also to admit to ourselves, boy, I sure would like to be able to test this. I strongly suspect that the multiverse exists, but I can't prove that the multiverse exists. So what was the beginning? I want you to take away that the Big Bang is real. The universe did begin from a hot, dense, rapidly expanding, more uniform state filled with matter and radiation. But that does not necessarily imply a singularity. You cannot wind the clock back to zero size and infinite density and t equals 0 and say we had a singular beginning to space, time, matter, and energy, because inflation occurred before the hot Big Bang. It set up the hot Big Bang, but because of its nature, because of this exponential expansion, anything that happened earlier than that final 10 to the minus 32, 10 to the minus 33 seconds of inflation gets wiped out from the visible universe. Wherever that information was back then, it's now way beyond our observable horizon, and we're never going to be able to see it. So questions like, how long did inflation last? How did inflation start? Did inflation start, or was it an eternal process? These are open questions. We do not have answers to these. And that's why I titled this talk, The End of the Beginning. So to give you conclusions, the Big Bang is a hot, dense initial state. The Big Bang is not a singularity. There may be a singularity, but if there is, it occurs before cosmic inflation. And we don't know what happened before cosmic inflation, including Was it just more cosmic inflation all the way down? You know, like turtles? Maybe. Cosmic inflation sets up the initial conditions for the Big Bang. It makes many other predictions that can go head to head against the Big Bang and have been observationally confirmed. I think it's a fun consequence, although it makes a lot of people sad. I think it's a fun consequence that it brings along a multiverse with it. But the sad fact is that the multiverse, as well as anything before the final 10 to the minus 33 seconds of inflation, is not observable. And this means for our universe, we can extrapolate it back. Expanding was hotter, denser, more uniform. You had the dark ages before the first stars and galaxies. You had this wall of neutral atoms, which looks like the cosmic microwave background, nucleosynthesis, hotter, 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 transition, inflation, and who knows? And that's the end of the beginning.
Wow, such a great talk. Thank you very much, Ethan. Just to echo one of the audience's expression, best layman explanation ever. Thank you very much. And I was watching the Q&A during your talk, and you basically answered every question that came along. But just for quick review and retouch, I'm going to ask a few of them if people need more explanation. One person asks, it seems to be assumed the universe appeared with no size, but is it possible that the universe originated with some size?
So what I can do, because I know how the expansion rate at any time and the energy scale of the universe are related, is if I can say, okay, let me calculate what the upper limit to the universe's temperature was at the start of the hot Big Bang. Then I can translate that into a how small at minimum was the observable universe when the Big Bang started. In other words, if I took all the matter and energy that we can see out to, 46.1 billion light years away, the limits of our observations, and I extrapolate it back to, this is the very end of inflation, the very start of the hot Big Bang, how big is the universe? If you had asked me that question just 10 years ago, I would have said the smallest it could have been was a soccer ball. Could have been about the size of a soccer ball. We have better observations now. And now I can tell you, ooh, guess what? I got to back up. The universe had to be about 4.5 feet, about 1.5 meters in size. And I'm hopeful that if we get better and better observations, we will be able to push that limit down and actually give you, maybe, if we're lucky, what the size of the universe at the birth of the hot Big Bang actually was. Right now, we only have limits. It could have been no smaller than about 4.5 feet in diameter. But I'm hopeful that in the future, we'll actually someday be able to give you a size.
Wonderful, thank you. And there are a lot of kudos coming your way in the chat. I hope you get a chance to enjoy them as well. Now, we have another question about conservation of mass and energy with respect to the expansion of the universe. If you can elaborate more on that, and then if the person says, if they're understanding correctly, how does that fit into the increase in the amount of or creation of dark energy with expansion of the universe?
Oh, this part, I'm going to disappoint someone today. I'm so sorry. Conservation of energy is such a good conservation law. Every interaction we have, every laboratory measurement we make, energy is conserved. Why? Why is energy conserved? In physics, there is a deep connection between symmetries and conserved quantities. right? Wherever you have a certain symmetry, it leads to certain conservation laws. So if I have a mirror symmetry, my left hand and my right hand are mirror images of each other, then if one does one and the other does the other, then I have what's called parity symmetry. Great. If I have mirror symmetry conserved, then parity is conserved. If I break mirror symmetry, then I break parity. What makes energy conserved? Well, there are two big things. Energy and momentum are always conserved in a laboratory experiment. Momentum is conserved because you have what's called positional translation invariance. If I'm here or there, or I'm invariant under boost, right? If I'm stationary and I see the same everything, and I'm in constant motion and I see the same everything, then momentum is conserved. And momentum is conserved in the expanding universe. What makes energy conserved? It's time translation. It's saying the universe is the same now as it was at earlier times and it is at later times. But our universe is expanding and cooling. So that means I look at my universe back then, and I look at my universe now, and I look at my universe in the future. And I say, oh no, my universe is not time translation invariant. Does that mean energy is not conserved in the expanding universe? Yes. Does that mean energy is not defined in the expanding universe? Yes. So you say, okay, I don't like that. I want energy to be conserved. So do me a favor, Ethan, ad hoc me a definition of energy that does make it conserved in the expanding universe. And I can do it. And I can say, okay, so now we have radiation, photons, and they're redshifting. They're losing energy. Why? Why are photons losing energy? And I can make an explanation to say, oh, it's because they're doing work on the edge of the universe, right? Work is force and distance in the same direction. So if the photons are expanding the universe, doing the work, like Porky Pig opening up the that's all, folks, then great. It's doing energy, it's exerting energy, it's doing work, and that's why it's losing energy. The problem is, if I say, how do I conserve energy for a universe full of radiation? And how do I conserve energy for a universe full of matter, which doesn't redshift? And how do I conserve energy for a universe full of dark energy, which is inherent to space? I need three separate definitions for what is energy. And so anything I tell you, if you only had one type of thing making energy in the universe, then maybe you can get away with that. But in a universe that has matter and radiation and dark energy, you can't define energy in a way that will make it conserved. So it's a good question. It's a question I get asked a lot, and no one's ever happy about the answer, but that's the answer.
Great, thank you. And the next question concerns anti-gravity. Is that a thing? Does that play a role in this? Could it?
So anti-gravity is an idea. One of the fun things for me about gravity is we know that matter gravitates, and we know that matter has inertia proportional to its mass. So one of the big questions people have is gravitational mass and inertial mass the same thing? There are experiments that have measured it to about 12 significant figures for matter, and it looks like it is. But no experiment has ever measured it for antimatter. And one of the things physicists are looking for is, if you could make a neutral atom of antimatter, which direction would it fall in a gravitational field? Would it fall down or would it fall up? In 2019, the year before the pandemic hit, I had the opportunity to visit CERN, which is where the Large Hadron Collider is. CERN also has a giant building called the Antimatter Factory, where they make anti-atoms, not just anti-protons and anti-electrons, but they trap them and bind them together and make neutral anti-atoms and manipulate them. And there are 6 different teams in the antimatter lab factory trying to measure what direction atoms and anti-atoms fall in a gravitational field. Almost everyone expects antimatter will also fall down in a gravitational field, which means anti-gravity still going to be theoretical only. But you have to do the experiment. Even though you think you know, you have to do the experiment, because if you don't do the experiment, you don't give nature a chance to surprise you. So keep your eyes out. There are 6 teams working on this. Most of them are back to work now at the pandemic, even in CERN, even with everything going on in Europe. So that's one of the results I'm hoping comes out, because I want to know, we know that matter only gravitates and doesn't anti-gravitate, but antimatter is a chance. Antimatter has a chance of anti-gravitating. And if it does, that's going to change everything.
Wonderful, thank you. And speaking of antimatter, do we know what caused the slight imbalance between matter and antimatter just after the Big Bang?
Oh boy, that's one of the biggest unsolved problems in physics. So if you do know, you should publish it and go to Stockholm, because everyone wants to know. I can cook up a scenario. I can say, okay, let's take, say, a grand unified theory where I have these super heavy particles and super heavy antiparticles that were produced in the early universe. And I can say, I can write down what conditions create a matter-antimatter imbalance. These were derived by Andrei Sakharov in, I think, 67 or 68. And he said, you only need 3 things. Number 1, you need your universe to be out of equilibrium, which means if your universe expands and cools and starts from a hot, dense state and gets cooler, you're out of equilibrium. So that one's done. You also need C and CP violations. So P is that parity, mirror symmetry, and C is charge conjugation symmetry, which means I swap particles for antiparticles. So if I violate those, and I also have interactions that violate baryon number, then I can make a matter-antimatter asymmetry. So I'll talk a little particle physics for a minute, just so you can visualize it. And I know you're recording this, so if you miss it, feel free to listen again. So imagine I've got a boson. I'll call it an X boson, and it has a charge of +4/3. And I make an anti-X boson along with it with a charge -4/3. And this thing can couple to both quarks and leptons. So if I'm +4/3, maybe I can decay to a positron, an anti-electron, and an anti-down quark. Right, so I'll have +4/3 for my charge. And then you say, oh, well, then the X has to decay to an electron and a regular down quark. And then I can say, okay, but X is +4/3. So maybe it could also decay to 2 up quarks, which means the anti-X has to decay to 2 anti-up quarks. So far, everything looks symmetric. But what CP violation means is what we call the branching ratios, or the fractions of the X that take path 1 versus path 2, and the fraction of the anti-X's that take path 1 and path 2 can be different from each other. So an X can be more likely to decay to 2 up quarks than to a positron and an anti-down quark. And an anti-X could be more likely to decay to an electron and a down quark than 2 anti-up quarks. So if I can make equal amounts of this type and this anti-type, but they decay unevenly, then I can wind up with just a little bit more matter than antimatter. And when all the things annihilate away and the dust clears, I can come out with a few leftover quarks and a few leftover electrons. And like I said, if you get 6 parts in 10 million, that makes the universe.
Fascinating. Thank you. And Now, you did talk about the curvature of the universe and how it affects its ending, ever expanding, or the big crunch. And also you mentioned that we've observed that pretty good the universe is flat. Now, but we also have inflation. The questioner wants to know if it's possible to have the opposite of that, a sudden contraction that results to the big crunch. Is that something possible?
So anything like a change in the expansion rate or a change in the energy content of the universe can happen abruptly if you have a phase transition. So a phase transition would be like, okay, so you remember I had that graph of I had a plateau and then I had like a well that you fell into. Well, what if one side of the well was a little higher than the other, right? So you fall into the high side of the well. There's a chance that you will be able to quantum tunnel into the lower energy state. Is this going to happen? I don't know. Some people think it might. They call this the vacuum decay catastrophe scenario, because if you tunnel from one state to another, that's going to change the 0 point energy of space, and that energy is going to have to go somewhere. The last time something like that happened, we got a hot big bang. How will this change the laws of physics? What's going to pop out of it? How will that affect the expansion rate? How will that affect the ratio of radiation to matter to dark energy? It's possible we could get an abrupt change that would change our fate. We think we're going to have a heat death, dark energy is going to drive the universe apart, flat forever, entropy wins, everything dies. But maybe not. We don't know. And this is a possibility we have to stay open to. I wouldn't necessarily believe the things that Paul Steinhardt and Neil Turok are writing about it, but it's always worth keeping your mind open, right? When we have an absence of evidence, we have to keep all the theoretical possibilities on the table. And this is one of them. So if you want to know, could we have a phase transition that leads to a recollapse? Yes, we could. If especially we right now have dark energy that behaves like a positive cosmological constant, if it were to decay to a negative cosmological constant, we would definitely recollapse. So it is possible that our fate will not be in the long run what we think it's going to be based on our past observations.
Thank you. Thank you. And the next questioner wants to know a little bit more about what black body radiation is, and if that could be caused by something, maybe a liquid at the edge of the universe.
Okay, so black body tells you how your energy is distributed. Black body is sort of this ideal scenario where if I took a perfectly black object, which means a perfect absorber, and I heated it up to a certain temperature, what would the spectrum of energy that it emitted be? And that's what black body radiation is. It says like, okay, here's how my intensity should look as a function of wavelength or frequency. So if you wanted there to be some sort of liquid, I don't think liquid is necessarily the best thing. What makes a good black body is a well-mixed plasma of evenly distributed energy everywhere. That's why if the sun had a hard surface and that hard surface was the same temperature everywhere, it would be a good black body. Because the universe had the same energy density everywhere and the same temperature everywhere. That's why it's such a good black body. But like I said, even this, the most perfect black body ever, it's still really only good to 29,999 parts out of 30,000. There's that 1 part in 30,000 imperfection in it. That's why we say the temperature of the universe is 2.7255 Kelvin. I don't even like putting that last 5 in there, though, because it goes up or down by about 1 or 2, depending on where you happen to be looking. So it is a really good black body, but it's related to a plasma, not a liquid or gas.
Great, thank you. Thank you. And the next questioner wants affirmation of something that he has heard, and that's the primordial stars could not have had any planets because their lifetimes were on the order of days, so no planets could have formed. Is that correct?
Part of that is correct. Most of that is correct. The part that's not correct is that they have lifetimes of days. That's not why you can't form planets. It's not because the stars have lifetimes of days. Remember, you might not remember, I brought it up pretty fast. The earliest stars could have only been made out of hydrogen and helium and like 1 part in like a billion of lithium. That's it. In that case, what's going to cool this big cloud of gas that has this energy that's going to collapse? Well, metals, astronomical metals, are normally the things that cool things. To an astronomer, you're hydrogen, you're helium, or you're a metal. It drives chemists nuts, right? Lithium is a metal, but oxygen is a metal, and carbon is a metal, and chlorine is a metal, and oh God, all the noble gases except helium are metals too. Yes. Yeah. Sorry, chemistry people. I'm sorry, but that's how we do it. So without metals, how do you cool it? The most efficient cooling thing that will exist is the rare hydrogen molecule that you get, H2. H2 will be the best thing that radiates heat away. So if you say, okay, I'm going to start with this initial spectrum of fluctuations, and I'm going to run my physics equations and evolve it, and I'm going to allow for hydrogen gas cooling, what will I get in terms of what I predict for the stars that should come out? Now, I'm hopeful that James Webb will discover these stars, and we won't be talking theory anymore. We'll be talking what we see. But right now, we have to talk theory. And for that, we say, actually, today, when we make stars with all the metals we have, the average star comes out to be about 40% the mass of the sun. The most massive stars will come out to be a few hundred times the mass of the sun. And if you average them all together, the sun is more massive than somewhere around 90 to 95% of all stars. So I know we get told that the sun is an average star, but really the most common star are these red dwarfs, and the sun is more massive than most of them. This is not true in the early universe. The first pristine stars should have an average mass that's about 25 times the average mass of a star today. The average star should be about 10 times the mass of the sun. And the most massive stars may be as massive as thousands of times the mass of the sun. The reason for this is you need to get a much, much bigger, more massive cloud of gas together to trigger its gravitational collapse than you need today, because it's so lousy at radiating heat away. So you need to get more and more and more of it to trigger that gravitational collapse. The reason the first stars don't have planets is because hydrogen and helium alone make terrible planets. We think you need a rocky core. We think you need those heavier elements. We think you need that to form seeds. Otherwise, you're either going to make a star or you're going to be a failed star. And that's it. And then these stars, they do have short lives, not days short. There's a fun, simple formula I'll give you. If you say the sun, with the mass of the sun, has a lifetime of about 10 billion years, and that's fine order of magnitude, then you would say, well, what if I doubled the mass of the sun, or made a star 10 times the mass of the sun. You might have heard, if you've seen Blade Runner, the expression, the flame that burns twice as bright lives only half as long. For stars, it's way worse. A star that's double the mass lives just 1/8 as long. The lifetime of a star is inversely proportional to its mass cubed, roughly. So if you're talking, oh, I'm going to make a whole bunch of stars. I say, yeah, how big's the most massive one? And you say, the most massive one is 1,000 times the mass of the sun. I say, oh, no. So instead of billions of years, we're talking decades, centuries, millennia. We're not talking about long periods of time. We're talking about a star that burns really bright, burns through its fuel in its core really fast, goes supernova, and emits a tremendous shock wave. And you've got some little rinky-dink, I want to be a Jupiter trying to form. We don't have that kind of time. That's why you don't have planets in the early universe, because the stars that they would form around blow up before you can make a stable planet without having those rocky elements to help you make it.
Thank you very much, Ethan. Now I've covered all the questions, and thanks for answering all of them. Before we end the meeting, do you have any final remarks to make?
I just want to thank everyone for being so receptive to hearing this story. I know that this is heavy stuff, but for me, this is some of the most wondrous stuff there is. And so thank you, Reza, for inviting me and giving the chance to share this little bit of the cosmic story with you. Thanks for your questions and your interest. And if you want a little bit more about what I'm doing, you should just look up Starts with a Bang, because that's what I do. So I've got a website, I've got a blog, I've got a podcast, I've got some books. You might enjoy them if you like this talk. I hope to be back, and I hope to get to share some more stories about the universe with you soon.
Definitely, we would love to have you back. Thank you again. And let me end this meeting by echoing yet another audience's view. They say, wow, mind has just been blown away. Thank you for blowing my mind. How refreshing, enlightening, and illuminating. So thank you very much again, Ethan. And let me remind everybody that you could check our calendar for all the events on our website at ocastronomers.org. See you all next month. Thank you for joining us, and we wish you great times ahead. Bye.